Hello pre-calculus class. In this video we are going to put together everything that we have learned in the last few weeks on polynomial functions and rational functions and limits and discontinuities, and put it all together in kind of our first calculus lesson, introducing this concept of an instantaneous rate of change, what we will come to call the derivative. So we're going to take a look at kind of through the lens of an example. A really common example that we use is kind of a position and velocity graph. If you've taken a physics course, you've kind of done some of this work already. If you haven't, that's all right. You're going to be fine coming right along with us here. We're picking an example, and the numbers of this don't turn out to be very realistic. This is a very slow bird here. We have kind of the situation, but just trying to put some sort of context to it to introduce this really key concept, right? When you start to do more modeling in real life, hopefully you will have some better realistic real world equations. But here we've been looking at polynomial functions, and we're going to continue to do that because that's one of the easiest lenses to kind of introduce this concept in, right? So we have this polynomial function that's modeling, in this instance, a bird that's perched in a tree 7 meters off the ground, swooping down and picking up her prey. So, right, if this is a time graph, right, my x-axis here is time, my y-axis is height. So this is not, right, like a distance thing. This isn't 2.5 meters away. It's 2.5 seconds later, right? But this is the graph she takes, so maybe going like straight down, grabbing it, and then coming straight back up. All right, so starting 7 meters up in the tree, leaving, coming down, and picking this up. So she has a flight path. This bird has a flight path, and we can answer some questions with that flight path. We can say, right, like what was the average velocity to that point? What was the average rate of change, right, from going from here, right, at 0 seconds, 7 meters off the ground, to 2.5 seconds later being only, right, 1/10 of a meter off the ground, just a few inches off of the ground here, right? And then what we want to be able to get to is saying, like, what was this bird's instantaneous velocity, right? Because it occupies a whole bunch of different velocities throughout this, right? We're stationary here at the start. We haven't moved yet, right? The bird's speed, the bird's velocity is 0 meters per second, right? Down here, where the bird is kind of turning around and going back up, again, temporarily, the bird, at least vertically speaking, isn't moving, right? Right before it turns back around, right? It stops there vertically and then turns back around and goes back up to the tree, right? And everywhere in between here is some sort of different speed. Right, we can talk about averages. We can look at, right, from here to there, what was the average rate of change, but everywhere in between there is a bunch of different speeds, right? Going, right, maybe here only like 1 mile per hour or 1 meter per second, and here maybe going 3 meters per second, and at the fastest part going 5 meters per second, and then slowing down, right, starting to pull up, grabbing it, and then leaving. So we're going to figure out how to do that. So first, let's build this average velocity, right? This is an Algebra 1 concept. Going back and just looking at average velocity, my average velocity here, right? This is just a change in distance over change in time that I'm looking at, right? What is the change in distance over the change in time for this thing? And so, right, in the case that we have here, right, my distance is represented by the y values, and the time is represented by the x values. So what we are really looking for is my change in y over change in x, which, right, is what's the y2 minus y1 over x2 minus x1. My change in heights and my change in times here, right? So if we're looking for, right, this average velocity between 0 and 2.5 seconds, right? What we're trying to find is, right, what was the y coordinate at 0 and the y coordinate at 2.5, and what's the x-coordinate at those 2 points. So I've already got these labeled here, right? My at 2.5, we're at like 0.125 meters off of the ground. So let's call that, right, my x2 and y2 here, right? So my x1 comma y1 is the point 0 comma 7, and my x2 comma y2 is the point 2.5 comma 0.125. Right? So if I'm trying to find this average velocity, right, another way that we can look at this, saying I'm looking at, right, what's the function value? Because this is the y-coordinate, right, at y2 is f of 2.5, right? And the y-coordinate at the first point at 0, right, is just f of 0. The x value of the second point is 2.5, and the x value of the first point is 0. So I'm looking at, right, this is again my change in y. This is my y2, right? This is x2, and this is my f of x2 is my y2 here. And here's my x1 and my f of x1, which is my y1 point there. Right? So numerically speaking, I can find this. Say this is my f of 2.5, my y2 is 0.125, my f of 0, my y1, is 7, divided by 2.5 minus 0. Do this math here. This is negative 6.875. Again, that's meters. Is my y is the height in meters here, I should say. Right. X is the time in seconds. Right. And this is 2.5 seconds. So my average, right, my rate of change here, and I'm going to move this over just a little bit because I need some extra room to write here because I already have the template set out. Right. This is negative 2.75 meters per second. That should be an S, not a 5. Right. Right. This is telling me that the bird, on average, between this point up here and this point down here, right, is going 2.75 meters per second down. Right, the negative indicates that it's decreasing. It's going downwards. Right, 2.75 would be the speed. Negative 2.75 is the velocity here. Right. And so this was looking at the velocity between two specific points, right? Our 0 and 2.5. We could generalize this, right? And we could try to figure out, right, what's the average velocity between any 2 points, like say between 0 and 1, right? This one, I could do the math really quickly here. It's going down 2 meters in that 1 second. So the average velocity from 0 to 1 would be negative 2 meters per second. And I could do the same thing for, right, any other points here. So let's generalize this. And I'm going to be specific with the lettering that I use here, right? Because to find the instantaneous rate of change, we first need to look at what's the average rate of change, right? So the average rate of change I want to move this up here just a little bit. The average rate of change for a function f over an interval between x and c. So we are using two different x values here. x being like my general x value, kind of this variable, this changing x value, and c is going to represent some fixed x value. So in this case, maybe right, my x was 0 and my c was 2.5. Right, we're looking at that change over some interval, x and c. This is given by a rational function r of x, r standing for rational function here. Again, it's just the same as what we did here, right? It's my change in y's over change in x's. So my y values, right, between x and c, right, the y value at like the point x is f of x. The y value at point c is f of c. And when I subtract one from the other, that gives me the difference here between the two things. So that would be like my change in y, right? This is just my change in y on the top. And down below, right, I'm just going to do my change in x, right? So all of this is doing is saying, right, between 2 points, 2 locations on this function, x and c, you can think of them as both being fixed if you want to for now, right? But eventually we're going to say, right, x is kind of this changing thing, c is this static, this one location. But this gives me that difference between the two things. So the book often calls this, right, and Mr. Leda especially will emphasize this when you get there, they call this a difference quotient. Right? Difference being subtraction, right, in the two things, and quotient being something divided by something else, right? Think of right, the quotient properties for our trigonometric functions, that the tangent of x was the sine of x divided by the cosine of x. That's a quotient. So this is the quotient of two differences, a change in y, y1 minus, or y2 minus y1, and change in x, x2 minus x1. So now we are going to use this concept to try to create this instantaneous velocity at 1 second. So at this 1 second mark, right, that's going to be our fixed point, where c is my 1 second, right? C equals 1. It's my fixed location, right? And I can find also my f of c. Again, you could get this by plugging it into here right off the graph, though I'm going to tell you that f of c is equal to 5. At 1 second, it is 5 meters off of the ground here. And so we can kind of model this average velocity around 1 second. And if we kind of get close enough to 1 second, we can get pretty good at doing this instantaneous velocity, right? So we've already talked about the average velocity between 0 and 1, right? It went down 2 meters in that 1 second. So the average from 0 to 1 was -2, right? If I wanted to get maybe a little bit better estimate, because again, right, it's kind of going really slow at the start here, and it's speeding up. So I don't think, right, it's not a straight line. It's not doing -2 meters per second the whole way. Here it's slower. Here it's a lot faster. So I would expect that my instantaneous velocity at 1, right, as this thing starts to, right, the line gets a little bit steeper as I get closer to there, is going to become a more negative number, a larger negative number. Right, maybe closer to this average velocity between 0 and 2.5, right? If I were to draw a straight line between those two things, that would kind of give me a good representation of that average change. To my eyeball, it looks like it might even be a little bit steeper than that average as well, right? So what we can do is we can model this a little bit numerically first, just to get a better picture. So let's go to Desmos, right? In Desmos here, I already have this graph created, again with the 0 and the 7, and down here, right, if I plug in 2.5, it's exactly 0.125. It's not quite the vertex, it grabs it a little bit before it hits that bottom there, right? But what we want to do is we want to try to figure out, right, like I have the points on there, right? Let's do 1 comma f of 1, right, which show that label. This is the point 1 comma 5, right? The bottom point is 2.5 comma f of 2.5. Again, show that label. That's right where we had it before. And again, my vertex, we've got that set. So we're trying to figure out, right, what's the slope of this curve here. You can actually see, right, it starts to go up a little bit first and then comes down, right? So if I look at the straight line between the two, right, that's that slope between this point and that point is a slope of negative 2.75 meters per second, right? We're trying to find this one. So again, if I went from 0 to 1, that's not a very good representation of that, right? If I were to, let's see if I can do this actually, this draw feature on here, right? That if I were to go straight through those 2 points, right, that's not a very steep line. That's a pretty shallow line. I want to know what's the instantaneous rate of change there, right? Like how fast is it at that exact location? Somewhere in between here and here, right? So let's take a look at that, right? If I got maybe a little bit closer, right, instead of going from 0 to 1, right, that shallow line, what if I got a little bit closer from 0? What if I went to like, right, 1/2, right? So this point here, right? Well, if I drew a straight line connecting those two things, right, this is a little tricky, right? But if I connect a straight line from here to there, right, like that's definitely a little bit better, right? And if I wanted to get a little bit closer, right, like let's zoom in on this thing, right? Right, playing around a little bit more, I've got the line tool, right? See, that's too shallow. If I went a little bit closer and did a straight line through there, that's definitely a better approximation. But I can get an even better one if I went in just a little bit closer, right? And did that right through those points. And I could get an even better one if I went just a little bit closer. And right, when I'm zoomed way out, this doesn't work super well. But if I zoom in, the more I start to zoom in on this point, the closer and closer it gets to looking like just some straight line where I could find, right, what is this change from maybe just here to there, right? And the closer and closer I get, the straighter and straighter it is, and I can estimate, right, pretty darn accurately what is the instantaneous velocity at that one point. So we're going to do that with that difference quotient that we created. So let's make that function, right? So I had my function that r of x is equal to f of x minus f of 1 divided by x minus 1. It's right, f of x minus f of c divided by x minus c. So that function, right, is this purple thing, which, right, looks a little bit weird here, but it would tell me, right, at 0, right, the difference quotient at 0, that rate of change from 0 to 1, was negative 2, right, from this point 0, 7, to the point 1, 5, that average rate of change from there to there was negative 2, right? And I can get in a little bit closer, right? That if I wanted to, right, go from 1/2 to 2, right? 1/2 to, 1, it's going at a rate of negative 3.25. And what I want to do is figure out what is it exactly at 1, but at 1 it's undefined. It has that hole. But if you're looking at this, right, and you did the work from last time, you can kind of get where I'm going, right? This is approaching something, right? If I want to create that hole, this instantaneous velocity here, I want to know what's the difference between 1 and 1, right? What's the change in y at 1? Well, that change in y is 0. I want there to be no change in y at that point. And what's my change in x, right? Instantaneously, what's the change in time? There's no change in time. It's 0. So what we're trying to do is create that 0 over 0 that we had from here, right? We want to make this happen, right? So let's do that quick numerically first here, right? So numerically, I can make a table, right? We'll add a table to this, And we want to just get closer to 1, right? So I want to do this x1, and I want my y values to be pre-populated for me. I can make that be my f of x1. And then I'm going to add just another table here with my r of x1 values, that rate of change, right? So my x1, let's do at 0.9, right? At 0.9, I have this point here, right? 9/10 of a second later, the bird is 5.389 meters off of the ground. The average rate of change between there and there, right, between 9/10 of a second and 1 second, it went down, right, 0.389 meters in a tenth of a second, which would be an average rate of change of negative 3.89 meters per second. But let's get a little closer. Right? Let's go to 0.99, right? There, again, if I zoom way in on this, right, at 0.99, it's at 5.04. It's actually, right, a little bit more. Desmos is truncating on the graph, but it's giving me a pretty good approximation here, right? And I get this average rate of change. That's this. It's going down, right, 0.039899 meters in 1/100th of a second for an average rate of change of this, right? And I can get a little bit closer yet there, right? And at 1, it's undefined. I cannot do that, right? Let's just populate a little something on the other side just to see, right? This is telling me what I'm getting closer and closer to, right? It's also telling me a little bit that this bird is speeding up, right? From here to here, it's an average of like 0.39 or 3.9, sorry, right? On the other side, it's going a little bit faster, going down 0.41 meters per second, right? But right here, what looks like it should be filling the gap, that would be its instantaneous velocity there. So I brought that difference quotient over here, and I did a little writing here because I just wanted to show, or to illustrate one time, what's going on here in this table, right? Because what this difference quotient is finding is like the change in y over change in x between some changing point and 1, right? So for this thing, this negative 3.89, that's going again from between 0.9 and 1. What's my y value at 0.9? How high up in the air is this bird? 0.9 seconds after it left. It's at 5.389 meters off the ground, right? What's the y value at 1 second? 5 meters. In between there, right, it went down 0.389 meters in a tenth of a second. The way my math comes out, it has negative time and this positive distance, but the rate of change is going to come out the same no matter what, right? Going to this, right, negative 3.89 meters per second is that speed from 9/10 of a second to 1 second, right? And I can do the same thing for each of these, right, algebraically, like actually doing the math. Some of the questions in the book ask you to do that. Do as much or as little of that as you want. I want you to understand the concept behind it here. And again, at 1 second, I end up with 5 minus 5 divided by 1 minus 1, right? There is no change in distance, and there is no change in time at that one instantaneous thing. But what we can do is exactly what we did in the last lesson, where we can find that instantaneous rate of change by finding this limit, right, of this average rate of change to that point, right? So, let's take some notes here. Sorry about the video editing, but I'm trying to get through this as kind of quickly as I can here, right? Find places I can cut corners. To find that instantaneous rate of change between any, like at any point C, in this case 1, we want to find the limit of the average rate of change between some changing x and that one fixed point C, right? And that limit has a name, right? The limit of that average rate of change as x gets closer and closer to C, as we're getting closer and closer to that instantaneous piece, we call that the derivative of the function at point C, right? And so we write that, right? This is written f prime of C, right? And for those of you who aren't watching the video, right, pronounced f prime of c. It's that same function notation, f of something, but right, we use that little tick mark up here, right, which I should maybe write this a little clearer, right? Kind of write it like that, f prime of c here. And that is, right, I can define that formally, that the derivative of something at point c, f prime of c, is the limit of that difference quotient, of that r of x, right? That change in y, f of x minus f of c, divided by the change in x, x minus c, as x gets closer and closer to c. And this is true for every function type, every exponential function, every power function, trigonometric function, polynomial function. This is a fundamental truth, that if I want to find the instantaneous rate of change at a point, I just want to find out, right, what's the change in y's and the change in x's, and just get them to get closer and closer and closer together. Right? So we can do this algebraically for that one. We kind of see, right, graphically, numerically, it should be getting closer and closer to -4, right? I can tell that here, but where does that come from? Right? Well, what we want to do is actually make, right, that equation, right? That we want to write out that limit. F prime of 1 is equal to the limit, as I bring my x values closer and closer to 1, between the change in x, f of x minus f of 1, divided by, or sorry, a change in y, f of x minus f of 1, divided by the change in x, x minus 1. So we can go back up and pull out, right, I know, right, my f of x from above was x cubed minus 4x squared plus x plus 7, right? And my f of 1 is equal to 5. So if I write this, my f prime of 1, this is equal to the limit, as my x values get closer and closer to 1, of f of x, write it out, right? It's x cubed minus 4x squared plus x plus 7 minus f of 1 is 5. Right? So this whole thing, like, I actually put in what is the function, right? My function is this, right? And this is the one static point, the f of 1. But I can combine these two things, right? Like the 7 and the 5, right? Just this last piece of the polynomial function, that constant, and the f of 1, those are like terms that I can put together eventually, right? Don't forget also, I need to do still the x minus 1 part, right? But when I simplify this, I get the limit as x approaches 1 of x cubed minus 4x squared plus x plus 7 minus 5 is just going to be plus 2 divided by x minus 1. And so I want to actually do this division, right? Divide this polynomial by that, and you can again do it polynomial long division style if you want. I'm going to do synthetic substitution of that 1 because it gives me the same result, right? So I'm going to do the synthetic substitution where my x is equal to 1, the value that would make this denominator 0, the value of x, right? That would be that factor. If x minus 1 was a factor of this numerator, x equals 1 would be a 0 of that function. Right? So I put in the 1 up here, right up in the top corner there. The coefficients of the numerator, 1, -4, 1, and 2. And we'll do that synthetic substitution. Drop the 1 down, multiply by 1. Right? Add those two together, I get -3. I multiply by 1, I get -3. Add those two together, I get -2. Multiply by 1, I get -2. Add those two together, I get 0. Right? So this function here, right, this f prime of 1 is the limit as x gets closer and closer to 1 of, right, this cubic divided by this linear function, I could rewrite as 1x squared. Again, these are the coefficients of that quadratic remainder, right, minus 3x minus 2 plus 0 divided by x minus 1, right? Again, this is just a shortcut to that polynomial long division. So these are my quadratic coefficients, and this is my remainder with that division, and I always put the remainder on top of that. But again, that 0 over x minus 1, that has no effect anywhere except at 1. 0 divided by anything is always 0, no matter how close x gets to 1. Right? 0 divided by 1/100000th is still 0. Right? So what I want to do is just plug in 1 to this quadratic remainder. Right? So this is equal to, just what is 1 squared minus 3 times 1 minus 2. It's going to be 1 minus 3 minus 2, or negative 2 minus 2, which is equal to negative 4. This is my instantaneous velocity. At 1 second. Right. And that is your first calculus lesson. Right. Right now we are only working on this with polynomial functions. Right. Like we've only done this with a polynomial function because that is how we kind of, like, it's the easiest way to get rid of that hole in here is kind of through that lens of polynomial long division here. But this is true for any type of function. This is the backbone of calculus. In calculus, you will basically do this exact same process with functions that are not polynomial, and you're going to need to do some different strategies, but every single one of these, like, I can actually create a derivative function. It's called derivative because I can actually derive this rate of change from any function type, right? Every single type of function has a derivative function and some specific rules that govern it, and some of those rules turn out to be pretty cool, I think. Right, so we just kind of did this for a polynomial function, but I just put together a little quick list of, right, this is, right, how to find that rate of change for a bunch of different types of functions. So some original function and then the derivative function or its rate of change function, right? It all comes from the function. So the sine function, I can find its rate of change using just the cosine function. And the cosine function, I can find its rate of change by doing the negative sine function. The exponential function, e to the x, its derivative is itself. The natural log function, the derivative of that is 1 over x, just nice and simple. A power function, I bring the power out front and reduce this by 1. All of the inverse trigonometric functions, think back to those times when we were doing like the geometric representations of inverse trig functions back in section 4-6. All of those rates of change, I can come kind of using those tips and tricks of those geometric representations of all of these things. So that's what next year holds, is trying to figure out, like, where do a lot of these come from if you're taking calculus. So yeah, get some practice in. I will have up answer keys, and I'll have up my, I'll make some video solutions to those answer keys as well, just because doing one question like this is tough to do that justice. So do the practice, and good luck.